Good morning everybody. We will continue our lectures. So, having defined distributions and some issues related to distributions and also distribution solutions, we have to develop some sort of a calculus. The idea is that even though we have defined a huge class of objects which includes functions and measures and many other objects, quite often we will still restrict to function spaces when studying partial differential equations, solutions to partial differential equation. The difference is that the solution space which we are looking may not be smooth spaces, it will be generally some sort of an LP or L2 and other spaces. So, integrable type function spaces. For that space, you functions from that space, you need to develop the differentiation, and the distribution theory precisely gives a platform for defining the derivatives, and the whole platform is available to us, use that one. So, what in this course you will see is generally function spaces only, but we do treat it as a distribution, so that we can introduce the concept of derivative. So, we have to develop what you do in function spaces as a distribution, we have to see whether all that can be defined, and that is what we are going to do. So, in the next couple of 3 lectures, I am going to introduce some important thing, a couple of important issues. One is the order of a distribution, and more than that we want to define how to understand distribution little bit locally, in the sense that you know what is the support of a distribution, because when you know that for the support you also should know what is the meaning of a function vanishes. So, you have to develop the what do you mean by a distribution vanishes locally or in an open set, and then the support of a distribution, compact support, and then the classification and identifying such subclasses. So, we will begin with the distribution order of a distribution. Okay. Let me start with the red. Okay. Order of a distribution. Okay. So, let us understand, let me recall few things. Suppose f is a linear operator on a normed linear space, operator on a normed linear space, and the continuity of f is basically equivalent to the boundedness of that one. That means when you say that f is continuous, that means f of x is less than or equal to some m into norm of x. This satisfies for all x. Okay. That this is precisely the boundedness, or it is also continuity. This implies the continuity on a normal linear space. This is for all x in x, but we are working with the d omega, which is not longer a normal linear space, it is a locally convex space given by an inductive which we have discussed a lot in our preliminaries, and given by a topologies defined on dk. So, I just recall these spaces dk of omega. Dk, this is C infinity functions with compact support with the topology defined as like an inductive limit topology, but that inductive limit topology comes from dkj. So, you are looking omega approximating by kj's to omega, and then dk. So, dk of omega is a C infinity functions, same C infinity functions with the support in a fixed set k. So, this is also a locally convex topologies given by a family of semi-norms. Okay. So, you have the direct way of defining that one. So, so there is an equivalent criteria. So, we will not be able to get exactly this kind of bound. So, if you want a operator T is in D prime, that means it is linear, T is linear, then I want to characterize what is the meaning of T continuity, right, the continuity, and this continuity can be written equivalent as an estimate. This is called the continuity estimate. I am not going to prove you here completely, but the proof is not that difficult. If you look back, the topology is defined on D, D, K, you can see that this estimate, continuity estimate, this we are going to use it, estimate. Maybe we will give a notation, continuity estimate. Okay, what is the continuity estimate? So, the continuity equivalent to for every compact set, K contained in omega, there exists a constant C which depends on this compact set, an integer, non negative integer, in fact integer n equal to integer greater than or equal to 0. Okay. N that also depends on K such that, so this you should prove it in fact. Okay. As I said, the proof is just comes from the topology of dk such that modulus of T of phi less than or equal to C, that means Ck depends on K into of norm of phi at Nk. Just recall that if you do not remember, the norm of phi at Nk is nothing but supremum of d alpha of phi of x. This supremum is taken over for all mod alpha less than or equal to Nk and for all x in k. Okay. So, these are the things which gives us semi norms on dk. So, and that is the topology defined by that one, and this is for all phi in d omega with the support of phi is in k. So, for all, so for a fixed compact set there is a finite integer n. That means, so the interpretation of this is to estimate for any particular phi, it is enough to have finitely many derivatives, but that the compact set changes the finitely many, this is precisely tells you this, if you look at it, this is precisely, this is only finitely many derivatives up to order nk. So, for a given compact set, that means for a given phi, it is enough to estimate T phi can be estimated with finitely many derivatives, and this is finite, this norm in k because support is in k, that is fine. And so, but as the compact set changes, the n may get changed, it is possible that n may can go to infinity. Of course, that is what if he is in d omega, the compact set can be different and different, the will tell you. So, the proof of this, the proof is basically T is in d prime is equivalent to basically phi T is in dk prime. We have discussed this a lot in the discussion. Okay, this is for all k, compact contained in k omega. Okay, this happens. Okay, so the d prime topology, as I said, coming from, and T from dk prime, and so that you use the continuity of d in dk. okay, and that is given by the semi-norms, and that boundedness exactly from the topology given by DK. Okay. So, if you want to have a precise details, probably you can see the Rudin functional analysis, the lot of details about locally convex topology and d omega topology are all well written there, and maybe you can also see Keshavan's book. Not that much detail, but some views you can get it. So, this estimate is important to remember. Okay. So, you have to write down this estimate. Okay. So, you remember these estimates. Okay. So, as I said, this n equal to nk can vary as k changes, but if there is a k, so distributions of order finite order okay. If there exists n equal to nk n independent of k, that means precisely tells that finitely many derivatives are enough to estimate for every phi, okay, independent of k. Then we say T is of finite order, and the smallest n is called the order of the distribution, Okay. So, let me give you a couple of examples. Look at Dirac delta and its derivative, k equal to 0, 1, etc. Recall delta 0 is delta. Okay. Are distributions of order, or maybe I will use another notation to avoid k, L distributions of order L. You see, delta to estimate, you need your already remarked that to estimate delta phi, it is modulus of phi 0. So, you need the knowledge of only phi, but when you go to delta L, it is some minor modulus of phi, the kth derivative of phi. So, you need the knowledge, the estimate, the supremum estimate of phi k on that. Okay. So, that is why it is precisely the distributions of order L. Okay. Not only that, all f in LP or f L1 log or LP log, whatever it is, are distributions of. So, delta is a distribution of order 0, you do not even need the first derivative. Okay. So, delta prime is distribution of order 1, okay, or distribution, and even measures, all the examples are given, distributions of order 0. Okay. So, here a very small example, this can be used, exercise delta L can be used to construct a distribution, can be used to construct a distribution of order, and a distribution of order infinity. Construct an infinite order distribution, infinite order distribution. That means finitely many derivatives are not enough to estimate T phi. Once more I repeat, because it is a very subtle concept. For every compact set, finite order is enough. As the order the compact set becomes bigger and bigger, you may see that you may need bigger and bigger number n to estimate. More and more derivatives may be required to do that. So, I want to make some more comments here. Some more means some general discussion. I want to understand the distributions of finite order discussion. That is what you have seen that. So, now insert dk. So, for any n, suppose t is of t belongs to d prime of order n, okay. And then recall these spaces, the compact CCN. That means this again you have introduced Dn, this is Dn. These are all saying functions differentiable up to order n, but compact support. So, naturally, and you know the topology there. Second, this is contained in d omega. So, it is exactly the same way you can define. Instead of using all the derivatives, you use only the derivatives order n. Okay. And then what it precisely says that t can be estimated with the derivatives of order n. So, t is a mapping, this is exactly you want d n omega. So, this implies if you look at its derivative, this space derivative which are all distributions oh sorry, I have written something wrongly. This should be the, no, that is correct, this is correct. So, this is contained in the it will change it, right. So, it will dn prime, you look at its dual. So, because it is a d omega is of course dense in dn, which are all we have seen it, and so its dual will be. So, you see this is a some sort of again is all distributions okay. So, T is a d omega to r distribution, though, and it is T is continuous in omega d omega, and you have that continuity estimate which you have seen, and in this continuity estimate here you need only finitely and which works for every k, is precisely telling you that T is continuous with respect to dn topology. If you really look at it, that implies T is continuous with respect to dn topology. That is the meaning of finite order, because n is enough for everything with respect to dn topology. That is the meaning of it basically. Okay. That means T is a mapping in a small space. This is what exactly you want. T can be extended to basically that is already dn prime. That is the meaning of this one. Okay. In other words, that implies so I am not using a different notation, the extensions, the natural extensions via density, we use the same notation. Okay. So, T is in basically dn prime. So, dn prime, so if a distribution is of order n, and then that T belongs to dn prime. Okay. And T cannot be extended to see at the same time T cannot be extended to a lower one dn minus 1 cannot be extended to dn minus 1 because dn minus 1 this is a bigger one. Okay. This you cannot do it because if you can extend t to n minus 1 then you get your continuity estimate with respect to n minus 1. But n is the order and n is the least number which you get it. You cannot go down, you need up to including the derivative of order n. That means t is not in dn minus 1 prime. Okay. This is the important thing. So, if you look at it your d here, this is your d u1, then you have your if you go you will have your dn some whatever it is d, or so let me put another dm. So, if you go further you will have your the class of measures, right, class of measures. Measures means Radon measures in the sense that CC prime, that is CC naught. So, you can go up to CC naught. So, D etc. you get it. Okay. So, precisely your D is intersection of your DL, okay, for all L greater than or equal to 0. And what is this says? So, what does that says? And so, this precisely tells you that T belongs to dn and if you take its dual dn prime dual, it contains because dn minus 1 dual will be smaller. The dual reverse it, the whole process. So, T is in dn prime minus dn minus 1 prime. So, if you reverse this picture you will see you have your d prime. So, it will reverse that one. So, the d prime is a very large set. So, you will have your d prime there and then you will have a something like dn dl dn something is a dn prime. So, it reverses. So, so you will have this dn prime. So, you will have your dn minus 1 prime and your t belongs to here. So, if you take my union of dn's dl prime or L will give you the set of all distributions of finite order, distributions of finite order. So, in view of order, so in view of this one, so this is decreases, all the dn's are decreasing to d and then your d naught prime d 1 prime are all increasing. So, you will you would like to see what do I mark it. So, let me write it here. So, in view of this one I want to see whether you get this one. So, your d prime, this is the question, do I get this one, right, dl prime, and that is wrong, right, because this is all distributions of finite order and the exercise tells you finite order d prime contains distributions of infinite order. So, this is wrong. So, what you only have is, so it will not catch all the thing. dl prime, okay, for all L greater than or equal to 0. Because you know that in fact this is a strict inclusion, the exercise tells you that you have distributions of infinite order. So, the question is that the other question, can we identify, can we get dl prime, the union of all dl prime as L greater than or equal to 0 as a dual, that is the question. So, can you get some x, that is can we write this is equal to some x prime with appropriate topology? Yes, you can do that also. So, I will not give all the detail. There is a so you can define on CC infinity of omega, on CC infinity of omega, we have defined the via the inductive limited topology, can define another topology, to get and to which we call, in that case we call that space as, we call CC infinity equal to df of omega, f to represent finite, okay, and df prime is equal to your union of dl prime L greater than or equal to. So, this is what the idea of defining this topology. So, remark, so you can do that. So, under the topology of d omega, under d omega topology, d going to dm is continuous. This is part of the topology, which we will have anyway seen it in that one. All this we have seen it, but we are doing this one. So, d game, but this is not the closest topology, but this is not the closest topology, So, df of omega on CC of infinity of omega define the closest topology for which these inclusions are continuous. So, that is what the, so define df of the topology on df of omega is the closest topology for which the above inclusions for topology for which the inclusions are continuous. So, all these discussions, so let me together consolidate it in terms of the, probably I will use another term, in terms of the inclusions. So, you have your d omega. So, let me see whether I can write everything. Yeah, you have your d omega, and that is contained in, so all this discussion df of omega. Note that both d omega and df of omega are CC infinity of omega, the topologies are different. So, this is contained in C infinity of omega. So, you have all these inclusions. At this stage you have your CL of omega, and you get, if you go, you will reach your the continuous functions. Okay. So, and you also have the inclusions d omega contained in again df of omega. So, this is without taking, here the first one is without taking the compact support. So, you can also the inclusions CC here, if you go like this, you get an inclusion compact support. So, include your compact support contained in omega, and again here you have CC naught of omega. And further you also have this contained in here, all that inclusions you will have. So, you have your inclusions here. Okay. So, you see, so you have all the complete inclusion here, and you can also write its dual now. If you take dual, what do you get it? The corresponding dual, if you take it here, you have your d prime. Now, it reversed, right. So, it will be in this. So, you see, this is the largest set df prime like this, and you will have dl prime if you go here, and you will have d naught prime. This is nothing but your measures. Yeah, this is this is also called dl. So, you will have dl prime, and this is also called your d naught. Yeah, this is so we have, this is the corresponding to this one. Okay. So, this is the dual I have taken. So, I can take the dual here. If I take my dual there, I get d prime of omega, and then df prime of omega, df prime, and if I go like that, and I will get my CL without compact support dual, and you get C naught dual. So, you have all the inclusions here, and what is this inclusion? So, the CL contains this one. So, that is DL. So, DL prime will be bigger. So, this will be in this. So, let me write down that in color. So, it will be, is that correct? This is CCL. So, that is not the correct one. So, because this is bigger, so this will be smaller. So, you have this one and you have that one, and this is the stage you get the set of all finite order distributions, finite order. Okay. So, you have your complete inclusion analogy where the distributions are. So, all the distributions of order finite order are done completely. So, probably I will stop here, and now we will do the support of a distribution, vanishing of a distributions and all that, and then the aim is that to classify, in the next class we try to classify the set of all compact distributions with the compact order, compact. And then you will also see another interesting result, every distribution with the compact set of is of finite order, compact support distributions with the compact set of order, and we classify. Again we classify as a dual. That is one of the advantage, we want to see that also as a dual, and dual identification is precisely meaning that you can extend such distributions to a bigger space. So, that it will be more information is contained there. Thank you.